Hello everyone, this is Jashwant here. I'm a PhD candidate at Penn State, and I'm going to be talking about my doctoral thesis, which is about minimizing costs and maximizing performance for the next generation cloud platforms. So, to give you a very high level overall view of what my thesis is trying to solve, so there are a lot of applications which are trying to run in cloud nowadays, and the applications which I focus are machine learning based applications because they are projected to have uh, exponential growth in the upcoming years. So these applications, when they run in cloud, there are different kinds of resources to run them, like virtual machines, containers, or even bare metal instances. So from all of these resources available, cloud tenants need to write their own resource management layer, which needs to handle the load balancing, auto scaling, resource selection policies, etc. And these have a direct impact on the cost, latency, and performance of running the applications. So my first task tries to focus on the cost and the provisioning latency problem of running applications on cloud. And the next task tries to focus more on performance of the application as a whole so that I can get maximum performance but at a reduced cost of running them in cloud. Now from the provider side, these resources which I rent are actually run on physical servers, and the cloud provider has his own resource management layer to do efficient load balancing and in-packing of these resources, which will impact the power, energy, and utilization of running his own data center, right? So the last task which tries to focus on improving the energy efficiency and utilization of public cloud data centers. So to give you a very high level view of each of the individual tasks I have, so the first task actually tried to propose a solution where we can blend two different kinds of public cloud resources for cost effectiveness. So more specifically, I was using serverless functions along with virtual machines to do cost effective auto scaling. So the main takeaway here was that new virtual machines take up a lot of time to provision. So serverless functions can be used in the background to offload requests when new virtual machines are actually being provisioned, right? So these two combined together was able to give a cost-effective solution such that the SLO violations which will result from new virtual machine startups were considerably reduced, and also reduced over provisioning of virtual machines. And the next task which I have here to give you an overview of that. So as I'm tackling a very specific machine learning application here, as you can see here that to do an inference in ML applications, there are different factors which will affect the cost. So Spark was able to handle the provisioning latency problem, but the inference performance by itself is dependent upon the model latency and the accuracy of the machine learning model I used to do the inference, right? So in this work, I try to improve this latency accuracy at a reduced cost. So to give a very high level view of the existing work in this space, there are the two most known works, Infas and Clipper. I focus more on Clipper because, as we can see here, Clipper has the most accurate solution and the low latency, but the cost of running Clipper is extremely high. That's because they use a technique called model ensembling, where multiple inference models together run for one single request. So we focus on ensemble learning, and what we try to do in this is that is there a way for us to reduce the number of inference models used in an ensemble, and can we develop efficient auto scaling policies such that the resources used to run these ensemble can be significantly reduced, and on top can we leverage transient instances like AWS Spot VMs or Google Cloud preemptive VMs to reduce the cost. This was the next task. So now the last part of my thesis was most focused on the provider side. I specifically look into serverless platform providers where they have a bunch of issues with respect to SLO violations and uh, the SLO violations which pretty much result from starting up new containers to run requests, and these new containers have cold starts associated with them, right? So not being aware of the what the actual application execution time is and what the response latency requirement for the user is, these platform providers make suboptimal decisions in provisioning containers to ensure the SLO of the applications. So here we identify that there is an ample amount of difference between execution time and the response latency, which I call as slack. So we do a slack aware queuing such that I can accurately determine the number of containers required to run my request. And in terms of container scaling to match the request load demand, we use both reactive container scaling and a load prediction based proactive container scaling models to ensure efficient container allocations. So these three tasks together, we try to solve both the cloud tenant side problem and the cloud provider side problem in terms of cost and performance. So I was not able to go over a lot of in-depth details about each of the tasks. So I would be happy to answer any questions regarding them in the Q&A section. Thanks for attending my talk.